Hello, my name is Trisha, and today I will be presenting my Project 5 Pharmaceutical Substances and Voice over PowerPoint presentation. In this presentation, I will go over a synthesis of a total of 8 organic reaction steps of a variety of pharmaceutical substances. First off, I will be talking about the synthesis of dapoxetin. In this step, we will be creating a ketone. We have a benzene ring and an acyl chloride that will be reacted together with an aluminum chloride catalyst. The first step of this reaction is to turn the acyl chloride into a good electrophile that will be able to break the aromaticity of the benzene ring and acylate the benzene ring. The aluminum atom of the aluminum chloride is electron deficient because chlorine is more electronegative. The chlorine on the acid is hogging the electrons from the carbonyl carbon, so the electron will be given to the aluminum and the acyl chloride loses the chloride, making it an acyl group. This forms an anion that is formed from the aluminum chloride. The loss of electrons on this means that the former acid chloride has a positive charge, is highly reactive, not too stable, and a very good electrophile that is resonance stabilized. The carbon of the carbonyl wants to react with the electrons from the benzene. The electron from the carbon on the benzene ring gets taken away by the acyl group. The former double bond is now bonded to the acyl group. The carbon that has lost an electron is now positively charged, so a carbocation. The benzene ring wants to go back to being aromatic. How this happens is that the chlorine of the aluminum chloride is able to give its electron to the hydrogen nucleus, and then the hydrogen's electron can be taken up by what was the carbocation. Therefore, the benzene ring is reformed and we have aromaticity again. The hydrogen on the benzene ring is substituted with the acyl group. The anion loses its electron and goes back to being a neutral electron-deficient aluminum chloride. And that's how you create 3-chloro-1-phenol-1-propanone. After 3-chloro-1-phenolpropanone is formed, step 2 of this reaction is a reduction reaction of a ketone with sodium borohydride. Sodium borohydride is really useful as it will reduce aldehydes and ketones. So what we're doing is we are breaking a CO bond and replacing it with a CH bond. This is what helps us classify this reaction as a reduction reaction. How this reaction mechanism works using sodium borohydride with the ketones proceeds in 2 steps. In the first step, the H negative detaches from the borohydride negative and adds to the carbonyl carbon. This is an example of a 1-2 addition. This forms a CH bond and breaks a CO bond, resulting in a new lone pair on the oxygen, which makes the oxygen negatively charged. In the second step, a protein from the methylene chloride, Lewis acid, is added to the alkoxide and makes the alcohol. We also form an OH bond during the workup. So in order to make the alcohol, the oxygen needs to be picked up by a proton from either water or acid that is added after the reaction is complete. Moving on to step 1 in the synthesis of adiphenane through a nucleophilic acyl substitution reaction of a carboxylic acid, which is this here. In the synthesis of adiphenane, there is a conversion from a carboxylic acid to an acid chloride. In general, a nucleophilic acyl substitution occurs by a 2-step mechanism. First is the attack of the carbonyl carbon atom of an acyl derivative by a nucleophile yields the tetrahedral intermediate. After that, the tetrahedral intermediate can then eject a leaving group. The carbon of the carbonyl carbon is a good electrophile. The electron pairs of the alcohol functional group on the diphenylacetic acid molecule attacks the carbonyl carbon of the thionyl chloride, and the alcohol functional group is now replaced with a Cl group. This is the attack of OH upon SOCl2. Then is the expulsion of Cl negative and deprotonation of oxygen to form a protonated chlorosulfide, which is a good leaving group that can spontaneously leave and form a carbocation. The CO bond breaks with expulsion of the Cl negative anion, which forms CO2 in an intimate ion pair. This is where the carbocation and a negatively charged leaving group remain tightly held together in space. Lastly, the chlorine can act as a nucleophile, which will attack the carbocation from the same face of the intimate ion pair. Overall, there is a loss of SO2 and a formation of an alkyl chloride. Next is step 1 in the synthesis of estrone through a functional group interconversion, which is specifically a reduction or hydrogenation of an alkene. Specifically, this is an example of an alkene addition reaction. In a hydrogenation reaction, 2 hydrogen atoms are added across the double bond of an alkene, resulting in a saturated alkane. The overall effect of such an addition is the reductive removal of the double bond functional group. So, as you see here, it's gone. The catalytic hydrogenation can take place in at least 2 stages. First, the alkene must be absorbed on the surface of the catalyst, along with some of the hydrogen. This is our catalyst here. Next, the 2 hydrogens shift from the metal surface to the carbons of the double bond, and the resulting saturated hydrocarbon, which is more weakly absorbed, leaves the catalyst surface. An important thing to note about the reduction reaction is when the hydrogenation of an alkene is occurring, it is a syn or cis addition of hydrogens across a CC double bond. Part A, step 4 of the oxidation of a secondary alcohol in the synthesis of dexamethasone. This is where a secondary alcohol is oxidized and is converted to a ketone. The hydrogen from the hydroxyl group is lost along with the hydrogen bond to the carbon attached to oxygen. At the second stage of a primary alkyl reaction, an oxygen is slotted in between the carbon and the hydrogen in the aldehyde group to produce a carboxylic acid. In this case, since there is no such hydrogen, the reaction has no further to go and it stops at just a ketone. The result of this reaction will be a ketone and a water molecule. So in step 3, in the synthesis of benazepril is an S-enter reaction. In step 3, the synthesis of benazepril is an S-enter reaction using a polar aprotic solvent such as DMSO. DMSO is used because it is polar enough to dissolve the salt format nucleophiles and also not interact as strongly with anions to hinder their reactivity. The role of DMSO in this reaction is to solvate the sodium cation. The mechanism of how this works is that the chlorine is a good leaving group and the N3 is the nucleophile, which will attack the position previously taken up by the chlorine atom. Moving on, for part C, step 2 of the synthesis of amrinone. This is a nitration reaction. Step 1 of this reaction is the generation of a highly reactive electrophile, and that is the nitronium ion from nitric acid and the sulfuric acid. Step 2 is the attack of the electrophile by the aromatic ring, which is rate determining step. In the first and rate determining step, the nitronium ion is attacked by a pair of pi electrons to give a carbocation intermediate. The last step is a deprotonation, where the base here can be the sulfonate ion. Finally is the synthesis of triamcinolone. This is a step 3 of a dehydroxylation. OSO4 is used as it usually gives a much higher yield, which is good in the pharmaceutical synthesis, but it's extremely toxic. This reagent gives a syn or cis dehydroxylation. Overall, what happens here is the addition of 2 OH groups across a CC double bond. This reaction works through a concerted process whereby 2 oxygens from the osmium interacts with one face of the double bond, and this generates the syn stereochemistry. This is the end of my presentation, and I hope that you enjoyed it.